So now let's look at a real life example and understand how this kind of works out, how this plays out. So what we are going to do is basically first do the same thing that we have done as of now. First we are going to read the CSV, and then we are going to convert the column that is basically representing the dates into the index, right? So that's what we have done here. So the next part is basically, once you have the data, then all you need to do is do the feature engineering, right? So in this case, what we are doing is basically couple of features. So one is we are not going to capture, obviously one part is to add the trend, right? So adding trend is basically adding the 0, 1 values, which we are going to do. Apart from that, we talked about we are not going to add any holiday features as of now. But we are just going to add a trend variable, and then to capture the seasonality, what we are going to do is, we had seen, if you remember the last lecture, we had seen that there was a lot of spike in Jan and like December and Jan, and then it kind of fell apart. If you remember the yearly pattern. So we are going to use yearly seasonality capturing features, and for that we are not going to kind of again, this is something ingenuine and intuitive that you have to think about. So in this particular case, we remember that January and December were the most important months, so we are going to just use a feature which basically says that if it's a Jan month, or if it's a Feb month, or if it's a December month, and probably some middle of the year month, say let's say July, right? June. So that's what we are going to use in this case. So this is a yearly. So for yearly capturing, in this particular case, so this is the corresponding data right now we have. So this is the Y value, this is the month, which is one that we use for capturing seasonality. And then for other things, for capturing the yearly trend that we have here, so the other kind of seasonality, we are gonna use a feature which says Jan. If the month is Jan month, or if it's a December month, or if it's a Feb month or a June month, right? In the first case, this is a Jan, this is basically starting off on July, so there's 000 for all of them. In case you can see here, probably none of those examples have one of those months, so that's why all of them are 0. But after this, probably in this case 1991, there would be the next example would be 12/1, and you can see that for yourself. In that particular case, you would basically have something that looks like 0100, right? Because the next example is the December month. And that's about the features. And then we added a lag feature, which is basically nothing but you can see this value is now here, this value is now here, and this value. So every value is lagged by one particular value, right? One unit. And the missing value in the first case has been replaced by 0. And we have added the trend, right? So we have done everything that we have discussed about. Also, as I have explained, you can do a lot more kind of to capture the seasonality. You can do a lot more interesting kind of feature engineering. A lag, obviously you can add lag 1, lag 2, multiple lags, right? It depends on to what is the thing you're comfortable with. Trend, there's nothing much to kind of experiment. You just have to add this particular 0, 1, 2, 3, 4. Now we are going to split the data into train and test. Now this is again something, keep your eye out. This is something which is different from your machine learning predictions, right? I have been telling you there are small things which are very different from machine learning prediction that we are going to do here. And this is again another thing that we are going to do slightly different from normal machine learning prediction. Because in normal machine learning predictions, you take your train and test and then you split them, right? Randomly. That's not what we are going to do in test. In case of time series anymore. In case of time series, we are going to split them based on date. So everything before a date is a train, because obviously if you kind of mix randomly, your training set consists of data from the entire data set, and your test is also from the entire data set, that really wouldn't make sense, right? Because then because you're trying to predict every moment based on the past moment. If your past moment is already part of the training data, then it really kind of doesn't make sense. So that is a concept of time series. In time series, you're basically going to look at the data and take a threshold. Everything above that date, before that date, is basically your training, and everything post that date is test. So that's one major difference. And now the other major difference, which is basically in case of time series prediction, what happens is basically you are using your lag features to predict your current values, right? So yt-1 is one of the independent features which you are using to predict yt. So problem with that is basically the error that you have while predicting yt-1 is there's an error, right? And that error kind of gets multiplied every time you are trying to predict yt. So the error in case of time series prediction is multiplicative, so you kind of want to reduce that. So instead of directly predicting or using yt, what you're gonna do is use a log of yt. That's pretty much another difference that is there from normal machine learning and time series predictions. So we have discussed two of them. One is the trend test split and the second one is using the log values. One thing to add is, apart from the log thing, you can also use something like a return value, right? So basically, instead of trying to capture the log values of each of y values, you can also basically try and predict the change in the value, change in yt and yt minus 1. So that way also, if you do that, you are not going to have the multiplicative effect. But apart from this two major things, which is basically using log of yt's and using a train test split based on date and not a random split, rest of the things are absolutely same, right? So in this particular case, you can see that we have taken log of the price values, log with log x plus 1. Obviously plus 1 is because there could be values which are exactly 0, and for that, if you take log x, then there could be values which are completely 1, and if we take log x, which is log of 1, it would be 0, so we can just add a 1 out there. And that's about it. Nothing much here. So again, kind of going over the 2 points, two things that we did separately from normal prediction: train test split, and instead of directly predicting y, we are predicting log of y plus 1, right? That's what we are trying to predict, and that's it. So that's mostly summarizes everything that we need to do about time series. So we have the time series dates now. These are your y values. This is the thing that you want to predict, and these are your different independent features, right? Everything starting from month here, going all the way to trend, right? So those are the things that you want to predict, and that's it. After that, this is the same thing that we have done here right now. So we have calculated the RMSE values. RMSE values is basically the mean square error. Linear regression, as you can see, is basically x train of all the features that we have discussed, and then you're trying to predict that. And RMSE you calculate, then you can see the model coefficient, the model weights, and then what you're going to do is basically try and plot the prediction and how the actual values look like. So this is the train data that you see here in light blue, and then after that you see in green is basically the one that is the original data, and the red is the prediction data, right? So you can see that there's a slight there's a good overlap out there, right? So at least the way it has picked up the trend is awesome, right? So you can see the red and the green lines are almost following each other. Obviously there are some small spikes here and there which it is missing, but that's about it, right? So let's take a moment to kind of realize that we just did what is the thing that we did separately from normal machine learning prediction? We just added features, right? That's about it. That's absolutely about everything that is there about time series prediction. You just did some more feature engineering which are absolutely specific to time series, which again is something that is just not limited to what we have taught. That again can be a lot of things that are there in the out there, and you can have a look at all of them. Think about all of them, but that's about it, right? So feature engineering is the only thing that we did separately, and there were slightly two other things that we have already mentioned which is different from normal machine learning. That's it. Rest everything follows as it is. The RMSE measure error, doing the linear regression and all of that, right? So now let's try and plot the residuals. So in this case, what we are plotting is the y versus actual. So these are here on the left, on the y axis you have the predicted values, on the x axis you can see the actual values, and you can see that they're fairly lying on a straight line, right? If they are lied on an exact straight line, y equals to x straight line. So if there's a 45-degree line that they have lied on, that's exactly what we want. But that's not the case here. They are not lying, but they're absolutely something. They are almost lying on a straight line out here, which basically is a good sign that we would have expected. Now let's try and plot the residuals. So what we have done is basically taken the residual values and plotted a histogram out of it. And as you can see, there are a lot of values which are around -3, -4, -5, and then there's a lot of values. Sorry, there are a lot of values around -1. There's a lot of value around -3, and then there's kind of slacks off on both sides. So this probably is not exactly a normal distribution. If you remember going back to your normal distribution assumptions and assumptions about residuals when we discussed today also, what are the things that we discussed, right? So we had discussed that they should be distributed around a mean with mean equals to 0, and they should basically be they should be not auto correlated. So let's first check about the mean part of things. So clearly in this case probably it's not exactly distributed around mean equals to 0, but yeah, it's close to somewhere around mean equals to 0. So this is fairly good model. All this basically says is that there's probably some still juice that we can capture out of this data, but as of now this is a good model, right? Because the errors are almost distributed around my mean equals to 0. And now let's see the autocorrelation kind of a thing holds or not, right? Autocorrelation thing was where basically or the heteroscedasticity assumption of normal of linear regression, does that still hold true? Which you can clearly see here is something that is holding true, because the error values are almost, there's no pattern among the error value and the date time value, right? So as your t increases, there's nothing like error decreases or error goes down or error increases, right? So error is randomly varying even if when your t increases, right? So which is exactly what we would have expected. So that means this is a good model which has worked. Now insights from the things, as I have already explained, the errors are random. They have a constant mean equals to 0, which is something that we would have absolutely, we were expecting that would be the case. It's not exactly 0, but it's somewhere close to 0, which is fine. That probably leaves some scope for improvement. And apart from that simple linear regression model and basic feature engineering, we have reached RMSE of 1.96, which is high as compared to ARIMA models. Now you would be asking, what is ARIMA model? Again, you can refer your additional resources link to understand what is an ARIMA model. But the good part about all of this is basically simple linear regression is interpretable, it's easy to do, and it's easy to explain people, everyone knows about it. So those are the advantages that come with simple linear regression, and that's why linear regression seems to be working perfectly fine in this case, right? So those are the advantages of using linear regression, and as I've already explained, we have actually achieved a good accuracy, good RMS using that. Now lastly, there are two papers that are not papers but basically libraries of sorts that you can have a look at. So one is TS-Fest, the other is Prophet. They are basically used for time series predictions. Have a look at them, understand that the links are there in the repo already, in the notebook already. Go through them, understand what they're useful for, and that's about it. But yeah, don't rely on much of these libraries, because you really don't want to kind of depend on libraries to generate features for you. You want to kind of think about them and kind of do your EDA, and from that basically figure out what is the feature you want to go ahead with, what is the kind of feature engineering you want to do. So that's a note of caution. But apart from that, that's all about time series. We are finally ending the time series thing out here. And as it probably by now you have understood, time series is not very different from machine learning prediction. There are just slight feature engineering that you need to do as compared to normal prediction task, and there are small nuances here and there, trend test split, and predicting using log values or predicting using return values, and that's about it. Nothing much more very different from your normal machine learning things. Good, thank you guys, thank you, and let's now head over to the assignment part.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.